Hello and welcome back. Today we're going to be looking at 2020 day 7. I think I solved this problem live back when I was doing the 2020 live solutions. My opinion of the problem has probably gone up since then. I think the biggest trick here is mostly around parsing. But there's a satisfying array-based algorithm that we can use to solve it. So that's what I'm going to be showing you today. In 2020, day 7, we are doing some traveling. This was the year we were doing our tropical vacation thing, and we're doing some luggage processing. Our input looks like this. This is the test input that we're going to be using while I show you the problem, and then we'll run it on the real input later. But basically, each line has two words for some sort of identifier for a bag. So we have like light red bags, muted yellow bags, etc. And they contain some number of other bags. Some bags don't contain anything. So like faded blue bags contain no other bags. So we're going to have to handle this. And the important color that we're going to be worrying about the most is these shiny gold bags. Part 1 basically says, okay, so if you kind of follow this tree or graph of all of these different bags, how many unique bags contain at least one shiny gold bag? So if we scroll up here, we can see that like muted yellow bags contain 2 shiny gold bags. So that would be one of the bags in our unique set. But then this like dark orange bag also contains a muted yellow bag, which itself contains a shiny gold bag. So this would again be one of the bags in our unique set. And then part 2 says, okay, how many bags total, not unique bags, but how many bags total does your shiny gold bag contain? So if we look at the problem input again, we see that shiny gold bags contain 1 dark olive bag, 2 vibrant plum bags. So that's 3 right there, 1 plus 2. But then dark olive bags also contain 3 of these, 4 of these, etc., etc. So you basically sort of, this essentially boils down to like a graph theory problem. So we construct a graph and we're doing like a search along the graph, and we're keeping track of the number of bags at each step, and summing those all together. To find the number of unique bags for part 1, it's the same thing, except we don't really care what the count of the bags is at each step. We just want the number of bags in the unique set that contains shiny gold bags. So that is the problem. Our first task is basically going to be to parse this thing, which is going to be kind of annoying. As you might guess, there's going to be a lot of string processing here. But since it's a graph problem, I think it would be cool to represent the graph as a matrix. I did that in one of my previous sort of recent videos on my favorite problem of all time. I think it was 2019 day 14, where we're able to represent a graph as a matrix, and then we're able to do some nice array-based algorithms on it to be able to do these searches. So let's get into it. And you'll have to bear with me because I changed my prefix key because I was starting to get it was starting to wear out my pinky to hit the tilde all the time. But anyway, okay. So as I mentioned, I already have our test input loaded up. I think it makes sense to split each one on spaces. We can do for each here. Great. So basically each row contains individual words. We can assign this to P, and then it makes sense to be able to get a vector of all of our unique bags. So if we look at each one of these rows, we have the first two words constitute a unique identifier. So we can just say for each, we'll do to take, write tac, great, and then we can enlist each pair to get a single string. So we have light red, dark orange, faded blue, dotted black, etc. And we can assign this to I for identifiers. Man, working with the font this big is a little bit weird, but hopefully it shows up well on the final video. Cool. Okay, so when we look at P, basically in order to sort of like parse this into a graph, which we're going to try and represent by a matrix, I'm going to use a similar tactic that I used in 2019 day 14, which is we basically pull out these numbers, which you can think of sort of like as weights in the graph. And then we're going to want to pull out these unique identifiers for each new bag, right? And if we pull out the digits and we pull out the unique identifiers, then we can construct some sort of function that we can use to construct the rows in the matrix. Importantly, we're going to have to be able to handle these no other bags. So it would be nice if this had like a 0 or something like that. So we're going to have to kind of special case that. So just remember that we have to handle that. Now, when we're looking at each one of these rows, the first 4 words here basically don't have any bearing on constructing the graph. We already pulled out the unique identifiers at the beginning. So the function that we end up writing, we'll just do for each 4 drop, and that will allow us to work with only the parts of the strings that we care about. And we're also going to have to, as I mentioned, special case these no other bags. But for right now, in our input, that's only the last 2 elements. So we can just do -2 drop, and that will give us a bunch of rows for that we can write our parsing functions on. So let's see about parsing the digits first. So we'll write a function. This will basically be like enlist W, and I'll copy this over so we can sort of see it iteratively as we work on it. So that just puts everything into a big string, and then we can pull out the digits like we do in many other problems by using quad D, which is a string containing all the digit characters. So we can do this, that pulls out the digits, and then we do a for each execute. And that gives us the numbers. Great. So if we look at this function, if we just want to specify that by itself, it can actually be turned into a train. We can just remove this and assign this to D. And now, if we replace this function that we were specifying with D, then it pulls out the digits. Great. Next, we're going to want to pull out the textual information. So like we want, light red, bright white for the first cell, and then like dark orange, bright white, muted yellow for the second cell, right? So we're going to try and parse this text. It's going to have a variable number of strings for each row. The way I did this is if we look at, so if we just take like the first row of P, and we can write some sort of function to work on this. You'll notice, so if we look at like iota length of W, and we can just do like W like this, and then if we transpose it, we get this. So this is the this is basically just the index of each one of these items in the list. But interestingly, if we do a for mod here, basically each one of these sections Oh, and I need to, sorry, for this to make sense, I need to do a for drop here. There we go. Okay, so for each one of these sections that we're going to be operating on, each section basically consists of 4 words, and our identifiers that we care about always occur at indexes 2 and 3 if we mod the indexes by 4. So we can do iota length w, 4 mods, and then we want to check to see if they're in the set of 2, 3, right? So we get a Boolean vector there, which we can use to partition our inputs, like so, and then we just do a for each in list to turn them into strings. Now, again, just like with our digit function, this can become a train. So this becomes a jot. We get rid of this. This becomes a write tack, and we can assign this to T for like text processing function, I guess. And now if we come back to here, then if we just do T, we basically get all of the textual identifiers, right? Okay, so now we're going to look at, so let's take a look at P again, and we'll construct some sort of function to do the digit parsing and the text parsing, and we'll start building matrix rows. I mentioned that we have to filter out these no other bags. A really easy way to do this, if you look at it, is these have a length of 3, as opposed to everything else, which will have a length of at least 4 if they contain at least one other bag. So we can say, first of all, we're going to build a row of our matrix, which we can do by just saying, for each one of our identifiers, we have a row 0, like so. We'll do each here. Great, and then, if we mix these together, we get a matrix of zeros. So, that's a good start. And we can assign this to like A, and then we can say, hey, if the length of omega is 3, then we just want to return the 0 vector. So these are basically rows that don't contain any other bags. Yeah, there we go. And so, we define our 0 vector, and then if they don't contain any other bags, we'll just special case it and return the 0 vector, right? Otherwise, we're going to want to do some modifications on the 0 vector, and the format that I'm going to use for this is very similar to what I did, again, for 2019 day 14. Basically, we're going to amend the 0 vector at certain indices, and we're going to place in the digits that we parse out. So the indices that we care about are going to be the textual identifiers of omega, so our text processing function T, and then we're going to do identifiers index of. And this will give us the indices of the different identifiers, and then we can just parse it with digits from omega. And that gives us this, and if we mix it all together, we finally have our matrix. So we can call this function here like B, I guess, and then our actual matrix will just be for each B here, and that will be our matrix. Great. So that's all the text processing done. As I mentioned, the parsing is sort of a pain. But now we have a nice matrix that sort of denotes the graph. And if we, actually I can demonstrate this, if we put the identifiers on the left sides, and maybe I can do like this along the top. Wow, this font is big, but whatever. So we can see that according to our matrix, you can read each row as basically, contains. So like light red bags contain 1 bright white bag, 2 muted yellow bags. Dark orange bags contain 3 bright white, 4 muted yellow bags, et cetera, et cetera. If we like mix P, we can sort of see this is our text input, just split it on spaces, and we can see that light red bags contain 1 bright white bag, 2 muted yellow, et cetera, et cetera. So our matrix seems to match up here. Okay, great. So here's our matrix. Now the problem is basically we need to do some sort of search. I think breadth first search is perfectly fine. And we're actually going to solve part 2 first. So if we come back and look at part 2, it's asking how many other bags does our shiny gold bag contain? And we'll come back and solve part 1 later. Just bear with me for a second. So for part 2, we could get the row of the shiny gold here, so like 5, and we can index into our matrix and we can get that row. And when we're talking about breadth first search, what are we actually doing? So this contains 2 other bags, and what would be cool is if we could take this row and have each one of these multiply a row in our matrix and then sum them together. So it contains 1 of this row, 2 of this row. So we would multiply by 1 and 2 these 2 rows, and then we would sum them together to see how many bags in total we contain at that step of the breadth first search. And this operation can basically be done using matrix multiplication. So if we do m plus dot times m, right? This so this gives us this is basically one step in our breadth first search, and we can actually construct a function here. So we could say we could do m plus dot times w power function. Let's say that we just run it once. This is equivalent to our last matrix. We can run it twice, and we get another step in our BFS. These are sort of the active nodes. We can run it 3 times. We can run it 4 times. And at this point, it zeroes out because there's no more nodes to cover. And, if we run this, 20 times or whatever, it's not going to change. So we can do a converge with power match, right? Now, the problem is basically each one of these steps is returning a discrete step in the breadth first search, right? And we could keep kind of like a counter matrix outside that we add to at each step, but it's actually pretty easy to do this. So if I just do, 1 time and we do m plus here, basically what this does is in addition to the breadth first search step, we add the initial weights. And that means that when we do breadth first search again, it's going to expand from the nodes from last time, but it's also going to sort of keep the values at each iteration. So we can add all the matrices together, sort of doing this. And now if we do a power match, we get a much more interesting matrix, which basically says, you can think of this as doing breadth first search from all nodes simultaneously. And so each one of these rows tells you how many bags that other bag contains, right? So I might be moving a little fast here. Bear with me. So again, if I do kind of like a concatenation of all of our identifiers here, essentially what our the matrix that we're using with breadth first search here, essentially what this says is, hey, light red bags in total contain 1 bright white, 2 muted yellow, 5 shiny golds, 5 dark olives, etc., etc. The row that we're most interested in, of course, is the shiny gold bag per the problem spec, and it looks like it contains 1 dark olive, 2 vibrant plum, 13 faded blue, and 16 dotted black. But yeah, so this is our matrix, and this can actually be simplified a little bit. Let's look at this again. If we do a commute here, this supplies an argument to the left side of the function. And the cool thing about arguments that are supplied to the left side of functions that get fed into the power operator is that they don't change from iteration to iteration. So you can just as easily do this. And if we're doing this, we might as well make this a train. So this will be left tack like so. And this gives us the same answer. Now, we defined our matrix all the way up here somewhere. Yep, here. And so we might as well just do, like, these few characters here basically encode the entire breadth first search algorithm. So we might as well just do it on the same row that we are defining our matrix. Okay, and then if we want the part 2 answer, this is basically I identifiers index of shiny gold, and we'll use that to index into M. That gives us this row, which tells us the number of bags, each type of bag that the shiny gold bags contain, and we can just sum those to get the answer of 32, which for the test input is correct. Now, part 1 is a little bit different. It asks you for the number of unique bags that contain a shiny gold bag. But what's really interesting, so first of all, let's make this we can make this a function, and again, this can be a train if we just replace this with right tack here. And so if we run f on m, that gives us our part 2 answer. But if we transpose m, this basically swaps the rows and the columns, and now the rows indicate how many times the bag is contained by another bag, right? So like shiny gold bags, if we just do this part, shiny gold bags are contained this many times by these other bags. But the problem is, we don't actually want the number of bags, we just want the unique ones. So what we can do is we can say 0 not equal to m, and this basically just caps all the numbers at 1. We can transpose it, swap the rows and the columns so that we're asking, which bags are contained by other bags, and we can run f on it, which basically just indexes using the shiny gold identifier and adds everything up, and we get 4, which for part 1 is indeed the answer. Yeah, so let's see. I wrote this down previously. When you put everything together, it looks like this. So just to recap, we read our problem input, we split everything by spaces, we take the first 2 elements and enlist them to get identifiers. We have a function that parses digits, and we have a function that parses textual identifiers. And these get used in a builder function where we basically create a 0 vector for the matrix that we're trying to build. And if the length of our input is 3, that means that there are no bags contained, so we just return the 0 vector. Otherwise, we change the 0 vector at the indices of the identifiers. We put the weights or the digits that we parsed out. For each row of our input, we drop the first 4 elements because they're not needed for parsing the sort of like the destinations. We run our builder function, and then we do the breadth first search using these 8 or so characters, basically doing repeated matrix multiplication and addition until we achieve convergence. And this matrix then has all the information that we need to solve both problems. We have a function that indexes into the row for the shiny gold bag, and it adds everything in that row. For part 2, because we're just interested in unique bags, we basically cap all the numbers at 1 and transpose it so that we only so that when we look at the rows, we're asking how many times is this bag contained by other bags, and then we count that up, and that's part 1. Part 2, it's sufficient to just run the function on our initial matrix. We don't have to do any sort of recalculation or anything. So yeah, that is that's 2020 day 7. And then if I run this on our actual problem input, we get 197 and 85,324, 197, 85324. So these are the correct answers for part 1 and part 2 if we're working on the actual problem input. Okay, now this is nice, this is concise. Basically, most of our effort is taken up in parsing. The actual breadth first search is just a handful of characters. This is certainly not the most efficient way to do things. So if we look at the shape of the matrix from our actual problem input, it's 594 by 594. And we're essentially like repeatedly multiplying this matrix against itself and doing some addition inside of our breadth first search. What we could do instead is we could have a function that's basically like, so we take the row of shiny golds, and we can index into that using, well, hang on. So we have this. Let me just sort of give you some timing numbers. So when we're talking about efficiency, so we'll pull in compx from defins, and we'll say compx, how long does this breadth first search algorithm take? And the answer is, looks like 34 milliseconds. So it's still quite fast. And just to make things even more one-to-one between the two methods that I'm going to be showing here, so we can assign this to this, and this matrix is then just our input without any sort of breadth first search applied to it. If we just do the breadth first search itself without having to build the matrix and everything, then it comes out to 19 milliseconds. Now, we could write a function, and that's going to be this function here, which we started building. So we pull out the row first, and then we basically do the matrix multiplication using just the row. So you can think about it like when we're doing the matrix multiplication against itself, we are doing a breadth first search from all nodes, which is a little bit wasteful because we don't care about all nodes. We care about one node in particular, which is shiny gold. And so we can do, instead of doing matrix to matrix multiplication, we can do vector to matrix multiplication instead. So if we do this, this will be like, so we have our vector, and then we're going to do some convergence here. And this is basically going to be W plus dot times commute right tack. I have to use the commute here because the train expects its rightmost element to be a function. And then we can do like left tack plus. So we're basically doing a vector multiplied by our matrix. And if I do this against M, I get a vector here. And then if I add it up, I get our part 2 answer. And if I do this, compx, this, and then these internal strings, I'm going to have to escape. This takes what is this? 63 microseconds. So if doing the full matrix multiplication takes 19 milliseconds, it's about 300 times slower. So for the problem input that we get for this problem, it's 19 milliseconds really isn't that long. It's certainly feasible to do the full matrix multiplication, but if the input was larger, then we could just take out the single row and do that instead, and we get a speed up of 300x in this case, but it would presumably be even larger if the input was bigger. The reason that I don't do it here is simply because the formulation is a little bit longer, and I really value concision in my solutions. Cool, yeah. So just some things to think about, performance considerations. So this is 2020, day 7. We're at what, 7 lines here. Yeah, I really like this this formulation of breadth first search by putting graphs together in a matrix. This is quickly becoming my favorite class of ablative code problems, which is basically like graph theory problems where the number of nodes is feasible to treat it in a matrix format, and then using almost like linear algebra stuff to do the graph traversals. I think that's really neat. There's a few of these. There's like, you may have seen like ands dot, sorry, I think it's or dot ands commutes for finding like the transitive closure of a Boolean graph. So there are some other tricks there. But yeah, this one also, in my previous video, like 2019 day 14, was another problem in this class. I think that these are neat, and it's going to be a technique that I'm going to keep in my back pocket for future ablative code problems. So, anywho, that is the solution and walkthrough. Hopefully you got something out of it. Thanks for tuning in.